Okay, so we've got this one of Newton's laws here, F equals ma, and we can also, well, really the way it's taught at GCSE is F equals ma, so force is equal to mass times acceleration. But once you get up to A level, and I think actually in some cases in GCSE nowadays as well, they teach that force is equal to the rate of change of momentum. And what we need to understand is that this is the same thing. So the way to understand how this is the same as that is to remind ourselves what is momentum. How do you calculate momentum? Momentum is mass times velocity, which we've got up here. So P is momentum, okay? And then we've got mass times mass times the change in velocity. There's no change in mass. Well, most of the time there's no change in mass. There are some cases when there is. For example, rockets when they move off, they leave behind a load of rocket fuel, and then there's a change in mass as well. But most of the time there isn't. So there's our change in momentum at the top, and there's a change in time at the bottom. But of course, the change in velocity divided by the change in time is acceleration. That's what acceleration is. It's how quickly velocity is changing. So we can change this bit here, delta v over delta t, and change it into a, and now we've got ma. So we can see that this is therefore the same as that. Okay. So I guess what we need to remind ourselves of is that the equation for acceleration. So how do we calculate acceleration? Well, so I'll just type it down here. Oh, don't think I need it quite that big. Let's try that again. Oh, come on. Oh, right, okay. Acceleration. Okay. I'm going to pause this because this screen recording software just will not, just doesn't work while I'm doing this. It's suddenly got. So the acceleration is equal to the change in velocity divided by time, but that's what we have up here. So instead of writing change in velocity over change in time, we can just write a for acceleration. And we've got m from earlier on, so this becomes ma, and that's what we started off with. So essentially, this is the same as that for that reason. Now we've got, but let's come back to our way of doing it before. We're using this version of the formula. So I think I'm just going to expand this frame a little bit. I'm going to introduce this idea of impulse. So what is impulse? Well, okay, let me just get something else ready. So we can rearrange it to be the change in momentum is equal to force times the change in time. Now that is basically what impulse is. So impulse is basically just the change in momentum. Okay, so which is equal to the force times the change in time. Now, but to the way that this is often, I mean, that's the definition of it. How would we actually apply this? Well, we might look at some questions in a moment, but often the way this is talked about is that if I've got a let's imagine I've got, okay, hang on a second. So what this diagram is saying is that as time goes along, there's a force applied to something. So this could be, for example, experienced in a car crash, right? So you're having a car crash, and what force do you experience on your body? Maybe something relatively high for a sustained period of time, and then eventually the car starts to slow down during the collision, and obviously the force reduces. Now, because the force is equal to because the impulse, the change in momentum, is equal to force times change in time. Well, whenever you have a crash, if you're going if we say the speed's always the same and the mass of the car is always the same, the change in momentum always has to be the same. You've got a particular momentum, and you're going and you're changing from that momentum. Is it going to? It's almost impossible to write on while I'm recording the screen at the moment. The change in momentum goes from the initial change in momentum and then it changes to 0. So the change of momentum is from whatever it was to 0. That's always going to be the case, whether you stop really, really quickly or really, really slowly, or whatever the experience of this collision is. The same can be applied to any sort of situation. So maybe a child falls off a climbing frame and is now moving through the air and hits the floor. When the child hits the floor, the child's momentum goes to 0, and so there's a change in momentum. Now, clearly, we can see from this diagram, from this equation over here, is if we extend the period of time of the collision, then we're going to reduce the force. In other words, if we have the momentum is going to be constant because we're slowing something down to a stop. But if we slow it down more gradually, then the force is going to be smaller, because when we divide a number by a large number, we get a small number. So if we did it in a short period of time, we're going to experience a high force, right? So let's say the change in momentum was 50 kilograms meters per second, whatever. Then it's going to go from there to 0. But if we do it in a short period of time, it's going to feel a higher force, or a long period of time, it's going to feel a smaller force. But what this graph is saying is that we could have a variable force over time, and the area under that curve is equal to the impulse, is equal to the change in momentum. Okay. Yeah, that's right. Impulse is the change in momentum. So basically, we could have a different kind of collision experience, couldn't we? Maybe it's not quite as smooth as that. Maybe the car isn't designed that well. So we could have something that might look a little bit more like this. So we could have a much more shaky kind of collision. Now, the area would have to be the same as the first area under the curve, because we're still reducing the momentum from whatever it was to 0. And so the change in momentum is going to be the same, which means the area under the curve has to be the same. So you can almost imagine like a piece of plasticine or Play-Doh, and you've got to mold it into shape. The volume of the plasticine must stay the same, but we would like it to not go high, because at this period of time, the person's going to experience quite a high force. Now, they didn't experience much of a force earlier on, but because of that, they have to experience a higher force at that point there in order to slow them down. So this is often the kinds of things that are talked about in impulse. Really, all about collisions and car safety and so on. So going back to the example of the child falling off the climbing frame, you'll notice that when you go to most playgrounds nowadays, they have a sort of soft floor on the ground outside, and that's because when you hit the ground, then it extends the collision time by a short period of time. Of course, we're still talking a very short period of time, but before, when it was like maybe a tenth of a second, now it's 2/10 of a second. So we're halving the force. Okay. So and of course, you can fall when you do fall yourself. There are clever ways to fall that absorb the impact. If you jumped from a high place with your legs straight, then that's not going to do you much good. Whereas if you bend your legs, you're gradually absorbing the impact, and so you're still reducing your momentum to 0, but you're extending the period of time, and so absorbing the impact more slowly, more gradually. That's basically what impulse is. So I'll just pause the video there. We'll have a look at some questions.